Hi all, thank you very much for tuning into my session. The session is on ozone technology. Now this session will be session 8B. In this session, I shall be discussing VOCs or Volatile Organic Carbons, TDS, Total Dissolved Solids, and half-life of a product. VOC means Volatile Organic Compounds. So these are organic compounds that, as the name describes, being volatile because they have a very high vapor pressure and therefore they emit the vapor. Very common examples of such organic compounds, they are acetic acid, butanol, carbon disulfide, ethanol, alcohol, formaldehyde, acetaldehyde, methylene chloride, xylene, and many aromatic compounds. Now, these are just carbonic compounds, carbon compounds which I'm discussing, but however, some of them can be complex molecules, like for example, perfumes or smells that are very similar in composition like perfumes. They are also volatile, they are also organic, so they come under the same subject. Plastics, for example, styrene, they emit special vapors. And chemicals in paints, petrochemicals, benzene, and very harmful vapors are generated in the chemical industries. Carbon dioxide and carbon monoxide, though that comes under the carbon, are not included as VOCs. VOCs are pretty dangerous. They can cause damage to health, and therefore it is very important that we try to ensure the VOCs in the atmosphere are as low as possible. As you see, there are many sources of VOCs, and many of them are not compatible with health. Now, if you look on the diagram on the right, which will give you some of the sources of the VOCs. We have quite a lot of fumes that are generated from motor vehicles and other equipment such as pumps, motors, etc., which may have motorized by either fuel, will produce these vapors. During the industries, when they react with chemicals, some of the byproducts can come out as VOCs, and many of the solvents that are used to dissolve materials, fats, etc., they also have got very high vapor pressures, and therefore they will emit the gases or VOCs. There are ways by which we can measure the VOCs, and we check on the atmosphere content of the VOCs to find out how polluted that particular atmosphere is. So it is very important, if possible, to reduce the production of the VOCs, and particularly in factories, we make attempts to remove the VOCs before we allow the gases escape into the atmosphere. The principal method for determination of volatile organic carbons is simply the sample that is taken into a flask, capped, and then a specific volume of the gas to be analyzed is drawn into a gas chromatography. The chromatography will analyze the different gases and give charts that will determine the concentrate of each of the volatile gases as compared with the standard charts. We will be able to measure each of the different components of the VOCs and provide a comprehensive picture of the contamination of the. Now we come to the subject of total dissolved solids, or TDS. The TDS consists of all the total of all the inorganic ions that are present in the water. The common inorganic ions that are present are sodium, potassium, calcium, phosphate, sulfite or sulfate, nitrite or nitrate, etc. The inorganic ions can be either positive or negative. The common organic compounds that also can ionize are acetic acid, tartaric acid, ascorbic acid, EDTA, and tannic acids. Because they can ionize into your positive and the negative ions. The most accurate measurements of TDS will be by evaporating a known water to dryness and weigh the residue. The weight will give the percentage of TDS in the weight of the sample taken. There is an approximate relationship factor between conductivity and TDS, and I will explain conductivity later in the slide or in this presentation. If you please refer to the publication by ResearchGate, that will give you some information between correlation between conductivity and total dissolved solids. Conductivity is the rate at which the electrons flow from one probe to the other in the conductivity probe meter. As the electron flow is the result of conductivity, which is actually the ability to pass electricity, the ions move from one part of the probe to the other when electric current is passed, and therefore the circuit is complete. The higher the conductivity, the faster or the more the electric current can flow from one probe to another. For example, if we add 1 gram of salt in 100 ml of water, that results in a specific conductivity. The addition of another gram of salt will increase the conductivity proportionally. We can measure the conductivity in Siemens per square meter. So there is a relationship between TDS and conductivity, which you will see in the next slide. And most conductivity probes or meters that we have, you will be able to select either you could get the information as a TDS or information as conductivity in Siemens per square meter. The chart on the right shows the relationship between the microsiemens conductivity and parts per million in TDS. you will notice is somewhat like a straight line. It is really not a straight line, but because we are taking a small portion of the white chart, it does appear to be a straight line. There is the relationship between TDS and conductivity is given in the equation on the left screen. The electric conductivity is EC. K is the conversion factor, and this is related to the chemical composition of the water, that is, what amount of solutes it contains. And usually the K is between 1.3 and 1.4. But because there is a temperature involved, the variation of the temperature will also vary the conductivity. However, for most practical reasons, we can just use a standard equation and the standard Ka constant and calculate the approximate conductivity or TDS from the given reading. You may not really read this because, as I did mention, most conductivity meters will be able to provide both microsiemens or parts per million, whichever you prefer. This slide has got the picture of a conductivity meter. The small probe connector you can see at the bottom of the meter that is connected to the wire, and the purple aspect, the whole probe is not visible, but it is part of a probe that will be placed in the water, and you will be able to read the temperature, the TDS, and the electric conductivity simultaneously. So whichever part you want, whether you want conductivity or TDS, you can easily measure with this meter. The little connector at the bottom can be connected to a computer where you can get it for charting. On the right, you have a portable probe, a portable conductivity meter with a probe at the end of the meter. All you have to do is you just take a cup of water or a cup of the solution that you want to measure and dip the probe, and you will be able to test the TDS or the microsiemens, whichever you decide you want to use. So it's quite a simple procedure to get this. So when we do water testings, we always ensure that we know the conductivity or TDS. It is quite relevant, particularly in cooling tower water treatment. It is quite necessary for me to discuss a little bit on half-life. Many of you would have heard the meaning of half-life, particularly in radiation of radioactive substances. Half-life can apply to many of other systems too, particularly where an activity or concentration over time is changing. The definition of half-life, it means the time taken for the matter or element to have half its strength after a specific time. In other words, if the half-life of ozone in the air is 20 minutes, it means the concentration of ozone in the air, if we say it's 100 ppb at time O, the concentration of ozone in the air after 20 minutes will be 50 ppb. That is exactly half. And after 40 minutes, it will be 25 ppb. That is half of that 50. And after 60 minutes, it becomes 12.5 ppb, and so on. So if you notice that the concentration reduced by 50% in every 20 minutes. So, for example, if you want to have, if you are told that a radiation of a particular product half-life is 5 years, so if you have 100 units today, 5 years time, it will have 50 units. 10 years time, it will have 25 units. And it goes on until it becomes almost zero. You can note that the half-life of ozone in water is much longer than the half-life of ozone in air. We have now come to the end of this session 8B. Thank you very much for having the patience to listen to my presentation. Please go to the next session 9, probably 9A, for basic cell structure, fungus, virus, etc. And if this is your first tuning in, please visit sessions 1 and 2, which gives you the complete program details, and sessions 3 to 8A. I would also appreciate if you click the like icon and the subscribe icon, as this will notify me the number of viewers that listen to my presentation, and also to notify you for future sessions that are uploaded as soon as they are done. Thank you very much, and have a very pleasant day.